Awesome. I expect we may hear a couple more dings in the next few minutes. People join in late, but we may as well get started. And if they miss a minute or two, they'll intellectually catch up with us. But Bill, thank you so much for joining us today. I'm really excited about this. This all got started when I was brainstorming what sorts of people we should invite on with my friend Jacob, who helps run the group. And we started talking about proof strategies and how there's all these different ways to go about proving things. And we were wondering kind of what the limits of that were. So I reached out to a prior guest of ours, Mel Andrews, and asked if there were philosophers who study this type of thing. And Mel suggested I reach out to somebody, and that person suggested I reach out to you, and now we're all here. So the ultimate topic is a little bit different from that initial seed, I guess, but still very related, and also relates to work at Northeastern, which is super exciting. So we're really excited to have you here, and I'll let you take it away, but thank you so much for joining us.
Okay, yeah, thank you guys so much. Really cool to be here. I like this talk, and I think I've only gotten to give it once before, and that there were no mathematicians present at the time, so I'm looking forward to this iteration. This paper is accepted for publication. It is not, I think, actually out yet. It's taking a very long time to be typeset and such, but if you want to read the final version of the paper, it exists, and I can send it to you. So great, thanks. And I think I saw Don. Don, very good to have you here. Nice to meet you. Thanks for coming.
Sure. Glad to be here.
Okay, so I think you guys normally do a shorter talk followed by a longer Q&A, which sounds great. I wish that I could do that. Unfortunately, I'm not sure that there's a great way to shorten this talk to 20 minutes or so. So we may have to do a slightly longer talk followed by a shorter Q&A. So apologies for that.
Yeah, that's totally fine. Whatever format works for you.
Okay, cool. All right, so without further ado, the topic of this talk is this. What is it that makes an informal proof acceptable to mathematicians? I think that's a really interesting question for both mathematicians and philosophers, one that has been debated for a long time. And in the recent literature, there are two suggestions that I think are particularly interesting. These have to do with the notions of transferability, which emerges from a debate started by Don and is due to Kenny Easwaran, and the notion of fixability, which is due to these two guys who I'll talk more about in a minute. Okay, so roughly speaking, a proof P of a theorem T is called transferable when it's possible for a typical expert to become convinced of that theorem solely on the basis of their prior knowledge and the information contained in the proof. A fairly well-known paper of Kenny's argues that transferability is in fact a constraint on acceptable proof. And on his view, the existence of this constraint explains why mathematicians reject so-called probabilistic proofs, even when those proofs confer a high degree of certainty on their conclusions. So the idea here is that probabilistic proofs, these are things like, there are like algorithms for testing whether a number is prime, where you can do a bunch of iterations of a test. And if it passes the test a certain number of iterations, you can be sort of arbitrarily confident that the number is prime, without ever reaching the sort of certainty that you get from a deductive proof, but with very high sort of credence, as high as you want. So the thought is that these kinds of proofs rely on steps that can't be captured in writing, like you have to generate a random sequence, for example, and then a reader of the proof doesn't have any way to check that that sequence really was randomly generated. All they have is the sequence, not the process that generated it. So these kinds of proofs aren't transferable, and hence they're not acceptable to the mathematical community. You can't, you won't convince your fellow mathematicians that some really big number is prime with the sort of certainty that we take to be sort of typical of standard mathematical practice, just by pointing out that you ran one of these algorithms. And I won't have much to say about Don's views, unfortunately, here today, but this whole debate that Kenny is responding to that sort of culminated in this notion of transferability is due to papers by our very own, or your very own, Don Fallis in the 90s and 2000s. So this whole debate and the talk that I'm giving wouldn't exist without his work. Okay, so that's transferability. The second main notion I want to talk about is fixability. So the idea here is that a proof is fixable when it's possible for other experts to correct any mistakes that the proof contains without developing significant new math. A forthcoming paper, which I like a lot, by Josh Habgood-Coote and Fenner Tanswell, points out that some acceptable proofs are both fixable in this sense and, in fact, in need of fixing in the sense that they contain non-trivial mistakes. So not all proofs are free of mistakes. Some of them, in fact, have pretty big mistakes, and yet that isn't necessarily an obstacle to their being generally accepted. So their main example, a theorem you may have heard of, the classification of finite simple groups, widely considered a theorem, in spite of, in fact, lots and lots of known and probably also lots of unknown errors in the existing proof, which, oops, I see some chat messages. Sorry, let me see what's going on here. Oh, okay.
Yeah, it's just a peculiarity of the screen sharing, but we can see the main content.
Okay. Can you not see me for some reason?
I can see you. Basically, there's just a gray bar on top and on bottom covering up what appear to be the Zoom controls from your perspective. But I don't think it's like meaningfully blocking material at this point in the presentation.
All right, thanks.
Yeah.
So one thing you might know about this theorem and its proof is that it's a really, really big proof that took like dozens of mathematicians, like thousands of pages of text to fully write down. That is true. Another thing that's maybe less well known about it is that the proof was messed up in all sorts of ways. In its original version, some of those gaps were quite enormous and required like hundreds of pages more to fix. Others are smaller, but still sort of rewriting the proof in a form that's free of all of these mistakes is still an ongoing process. Nobody thinks that all of the mistakes have been caught and fixed as of yet, and yet nobody seriously doubts that this is a proven theorem. So, okay, so I think like intuitively these are both quite plausible ideas. The claim that acceptable proofs have to be transferable, that seems quite plausible for reasons related to these kinds of probabilistic proofs that Warren talks about. Also, I think the claim that some acceptable proofs need fixing also seems pretty plausible. I was convinced by those two things the first time I read them and thought about them. The thing to notice that all of the rest of this talk flows from is that these two suggestions actually seem to stand in a sort of tension. So I'll explain why, but in order to do that, let me first give you some terminology. Okay, so I want to talk a little bit about different ways that a proof can have flaws or mistakes. So I'm going to give you some terminology which will be a bit pedantic, but then fortunately I'm mostly going to forget about it once I've said what I need to say. So don't sweat this stuff too much. Okay, so the first notion I want to say that an error in a proof is substantive if the way to fix that error wouldn't be routine and immediately obvious to an expert. So there's some amount of sort of thought or effort involved in fixing the mistake. It's not just a typo or something. And let me say that an error is fatal if the error renders the argument as stated incorrect. So you've got to fix it or else the argument doesn't work. Okay, so if a proof has at least one mistake that's both substantive and fatal, I'm going to call the proof broken. So the intuitive idea is there's a mistake that you've got to fix or else the proof doesn't work. And it's not just some sort of trivial, insignificant typo. It's like a real mistake that takes some work to fix. Okay, so I want to ignore other kinds of mistakes because they're not very interesting. Okay, so the main thing I want to take away from this is the notion of a BF proof. That is one that's both broken in this sense. It contains one mistake that has both of these properties, but also fixable in Habgood-Coote and Tanswell's sense. So it contains at least one serious mistake, but experts could correct all of its mistakes without having to develop significant new math. Okay, so now using this notion, more precisely, the thing I want to argue is this. There's a tension between the claim that all acceptable proofs are transferable and the claim that some BF proofs are acceptable. Okay, so I'll unpack that a bit later. Okay, so the tension then is this probably pretty obvious to you already. On the one hand, there's this idea of transferability, right? That says everything that, a suitable, well-informed mathematician should need to become convinced of the truth of a theorem should be contained in the proof of the theorem. But that isn't the case with the broken proofs, because these kinds of proof contain substantive errors. So then a reader is going to have to do some work of her own, maybe a lot of work, to identify those mistakes and figure out how to fix them. So since some of those errors are fatal, the proof isn't going to go through unless you figure out how to fix them. So these kinds of proofs aren't transferable. Hence, these things I'm calling BF proofs are not transferable either. Okay, so following this reasoning leaves us with a dilemma. On the one hand, either transferability isn't a genuine constraint on acceptability, so this plausible claim of Ease-Warren's is wrong, or BF proofs are never, in fact, acceptable, which would seem to conflict with things like the classification of finite simple groups being accepted. Okay, so what are we going to do with this? There's a bit of a puzzle here. I want to discuss several things that we could possibly do and talk through the various options, argue that most of them are non-starters, and in fact, there's just one appealing way to go here. So I think it'll be convenient to treat this argument as a reductio ad absurdum. And then what we can do, our job is then going to be to identify the false premise or premises of the argument. So reductio means it proves a contradiction. Any argument that proves a contradiction has to have a false premise. So what's the false premise here? So here's the argument in reductio form. First premise is what I'm calling the BF thesis. Some broken yet fixable proofs are acceptable. Second premise, okay, so take a proof like that, P. Then, since that proof is broken, it's going to contain fatal errors that require work to identify and fix. Premise 3, if a proof contains errors like that, the proof isn't transferable. So in particular, this proof P isn't transferable. Finally, there's Ease-Warren's transferability thesis, which says that all acceptable proofs are transferable. But then putting 2 and 4 together, we have that this proof P is transferable, yet premise 3 says that P is not transferable. So that's a contradiction. So at least one of these things has to be wrong. So we'll figure out which one it is. Okay, so there are 4 main options here. 4 main potential problems. First of all, you could just reject this concept of BF proof and insist that, in fact, brokenness and fixability are just incompatible. If you've got a broken proof in the sense that I described, then it just can't possibly be fixable, just as a matter of conceptual necessity. Second, we could deny this BF thesis, premise 1. Third, we could deny premise 3 and say that, in fact, all BF proofs are transferable. Finally, we could deny Ease-Warren's transferability thesis and say that, in fact, there are some acceptable proofs that are not transferable. Okay, so I want to consider each of these, and spoiler, in the end, I'm going to argue that, in fact, premise 4 is the problem here, that Ease-Warren's transferability thesis is the false statement in the bunch. And I'm going to suggest that it's not transferability, but just a weaker constraint that I call corrigibility that proofs have to satisfy. Okay. So again, the plan for the talk is to sort of go through these options in turn. And for the first three, I'm going to argue that these strategies don't work, leaving us only with the fourth. Okay, so this is option one. Reject this very concept. So why would you do that? So the thought here is you might just be suspicious, again, that the property I'm calling brokenness is compatible with the property of fixability. So if you think that those two things can't ever go together, then you'd also reject the claim that some BF proofs exist. So here's the basic idea. So I said a broken proof by definition takes substantial work to repair, but if it takes too much work to repair, then repairing it is going to go beyond experts' capabilities, and so the proof will no longer count as fixable. So maybe it's unclear that we can have it both ways at once. So if you're really skeptical of this claim, you might argue in the following way. You might say, look, fixing a broken proof, again, by definition, requires creativity and original thinking. But creatively generating a novel piece of a proof, well, that's basically like devising significant new math, and a proof whose errors require new math is unfixable by definition. So these two things aren't compatible. So I think actually this argument doesn't work. It sounds plausible, but I think it doesn't work, and I think the conclusion is wrong. And the reason I think it's wrong is because I think it wrongly equates one kind of inventiveness, namely the sort of insight you need to see how to fix a problem using techniques that already exist, which is, a genuine kind of insight, with a distinct kind of inventiveness, namely the kind you need to create entirely new math. So I think a broken proof can easily require the first thing without requiring the second thing. So there's a kind of illicit conflation going on here. So in case you're still skeptical, let me give you a couple historical examples. Maybe that'll make this sort of abstract terminological shuffling a bit more clear. Yeah, Ankit, you have a question?
Yeah, we are. So I have a question. Are we still assuming that the mathematician is sufficiently knowledgeable, and by that can he or she create the new branch of mathematics required to fix the proof?
Mm-hmm. Right. So if you're asking about what the notion of fixability requires, it's supposed to be specifically that you don't need to create new math to fix the proof. So
okay.
So take a typical expert in the relevant field, then whatever mistakes the proof contains, that person should just be able to figure out how to patch up whatever mistakes there are without having to do a bunch of sort of creative, original work. They can just sort of draw on what they already know and what techniques already exist in the literature. Does that make sense?
Yeah. I was assuming that I could prove P equal to NP by writing true and then giving you the onus of proving it or fixing it. But okay, so that
that presumably wouldn't be fixable in this sense, because we're going to have to come up with some new math to prove P not equal to NP.
Okay, thank you.
Yeah. Okay, so again, let me give you a couple historical examples just to make this a bit more concrete. So one nice example is Jordan's curve theorem, which I assume most of you have probably seen before. This is a classic and intuitively very obvious statement that nobody even realized you needed to prove until the 19th century when Jordan came along and tried to prove it. So this is the statement that a simple closed curve like these ones on the left divides the plane into two disjoint regions. So this proof has an interesting history. Pretty much everybody agrees that Jordan's original proof, which was given in his famous analysis textbook, wasn't completely In fact, the original reception was like quite strongly negative. People thought that it was totally wrong, totally hopeless. And the first people who actually gave a widely accepted proof used completely different methods. They thought that Jordan was like way off on the wrong track. But more recently, people have gone back and looked at Jordan's proof, started to think about it again, and they've come up with a more positive assessment. In fact, now lots of mathematicians think that the original proof did have flaws, but those flaws were actually quite modest and very repairable. So one person who's worked on this, Michael Rieken, says, Jordan's proof doesn't present the details in a satisfactory way, but the idea is right, and with some polishing, the proof would be impeccable. And Michael Hales actually goes to the trouble of presenting a modernized version of the proof, and he says that his version aims to preserve all of Jordan's major ideas while avoiding the original proof's minor shortcomings. So the current consensus as of the 2000s is that the original proof was flawed, but it was mostly sound, and that fixing the mistakes that it contains doesn't require any big new innovations. Okay, so that's one example that brokenness and fixability can go together. Second example, Perelman's proof of the Poincaré conjecture. So famously, Perelman was awarded but refused a Fields Medal and a Millennium Prize for proving the Poincaré conjecture in the early 2000s. What I think is a little less well known is that his papers really are more of a proof sketch than a complete argument. Since he first released his papers in the early 2000s, a few groups of mathematicians have worked on turning his ideas into something more like a completely compelling proof. And in the process, they found a number of mistakes in his arguments. But again, it's generally agreed that all of those mistakes are fixable. So here's a statement by one of these groups. They say, regarding the proofs, his original papers contain some incorrect statements and incomplete arguments, which we've attempted to point out to the reader. We didn't find any serious problems, meaning problems that cannot be corrected using the methods introduced by Perelman. Another pair of mathematicians working on sort of modernizing Perelman's proofs say that in spite of the need for repairs, full credit for proving the conjecture goes to Hamilton, who is a sort of important predecessor, and to Perelman. Okay, so I take it the cases like these show that BF proofs exist in practice, not just in theory. So if you want to have an example to keep in mind, you can think of one of these two cases. I think nicely, they also suggest that this notion of fixability is tracking something like mathematicians' judgments about acceptability. So it really does seem that what determines whether a proof contains sort of quote unquote serious problems and whether the author deserves credit for having proved the theorem is in part whether the errors in the proof can be repaired using existing techniques. I think that gives some helpful reassurance that this criterion actually captures a genuine element of mathematical practice. So I think Habgood-Coote and Tanswell are not totally on the wrong track here. Yeah, sorry, that was Jared.
I saw what your next section will be, and I think my question will be more relevant to that, so I'll hold off.
Okay, cool. Okay, so that is the first option. That is why I think, in fact, the strategy of denying the coherence of the very idea of broken yet fixable proofs is a non-starter, because I think we can point to concrete examples of proofs like that. Okay. Okay, so moving on to option 2. So option 2 is deny the statement I'm calling BF thesis, which says that some BF proofs are acceptable. So you could say that's wrong. In fact, none of them are acceptable. So maybe this is the most immediately appealing one. So you might think, well, why should we think that the mathematical community would ever knowingly accept a proof that contained serious mistakes? It seems plausible that they just wouldn't, right? Why would you accept something that you know has a major flaw? That's not sort of the standard we normally think of as what the one governing mathematical practice. Okay, so I'm going to argue that this is wrong, but before I do that, let me say a bit more about what I even mean by acceptance in the first place. I think this is a good time to do that. Okay, so when I say that a proof is accepted as a proof of some theorem T, what I mean is that the relevant experts consider P adequate to establish T. And as these cases we just talked about suggest, I think some sort of key signs of a proof's acceptance are things like this. The proof is published in a mainstream journal. The discoverer of the proof gets credit for having proved the theorem. Other mathematicians are happy to cite or use the proof as a proof of the theorem. So these are the kinds of things that I have in mind when I talk about a proof being accepted or acceptable. So in particular, if you've got a theorem that's regarded by the community as proven, then there's got to be at least one accepted proof of T.
In contrast,
so again, I think it's pretty easy to see why BF proofs might seem unacceptable. Because after all, they don't give complete correct arguments for their conclusions. And, it's very natural to think that whatever else an acceptable proof has to do, it at least has to do that. It at least has to give, a good argument. That seems very intuitively compelling, I think. But I also think that if you sort of stare a little more closely at mathematical practice, you find that that is not, in fact, quite what is going on. I think actually mathematicians are often pretty happy to accept flawed proofs, provided, sort of importantly, that the problems aren't too serious and that someone knows how to fix them or could easily enough figure out how to fix them. So I think actually what we find when we look carefully is that the standard for proof acceptance is closer to something like, well, we're pretty sure it's correct in outline, rather than, we've looked at every single detail and we've confirmed that every one is just right. So one way to see this if you're still skeptical is by thinking about how refereeing works for math journals. So in fact, referees are not generally expected to check every single line of a submitted proof. And in fact, most don't do that. And there's no secret about the fact that they don't. So one mathematician says, I think most papers in most referee journals are not refereed. There's a presumptive referee who looks at the paper, reads the introduction and the statements of the results, glances at the proofs, and if everything seems okay, recommends publication. Some referees do check proofs line by line, but many do not. There was also an interesting survey of math journal editors. And in a survey of those editors, they said that estimating the novelty of results was a more important task for referees than checking the correctness of results. And about half of those editors said that referees should check some, but not necessarily all, of a paper's arguments in detail. Also, the philosopher Lena Anderson, who has some interesting work on this, did interviews with mathematicians about refereeing practices, and she also found them to be more focused on sort of overall believability rather than local accuracy. So summing up her interviews, she says, when a referee checks a proof for correctness, she usually doesn't check every step. She begins by holding the proof, considered in broad outline, up against the landscape of what she knows. She checks whether each sub-result of the proof seems reasonable. If so, she will usually not go on to check the subproof line by line. She then turns her focus to the parts that stand out as surprising or suspicious. These are the parts she typically checks line by line. And Anderson concludes that published proofs often contain minor errors, but it appears that they rarely contain critical or unrepairable errors. And this is exactly the sort of claim that I want to make. Right? So if BF proofs were sort of generally looked upon as unacceptable, it would be really surprising for mathematicians to have this kind of attitude toward refereeing and publication. Maybe let me just finish this point, John, and then you can go ahead. Right. So the point is the fact that the discipline seems to show so much tolerance for fixable errors in published proof. I take that to be pretty strong evidence that these kinds of mistakes don't undermine acceptability. Right? You'd expect editors and referees to be way more fanatical if it was super important that there was never a mistake in a published proof. But that's not, in fact, what we see. So again, I mentioned this before, but one sort of very clear example of this is the classification of finite simple groups, which contains lots and lots of mistakes. People still seem pretty fine with it because we're pretty convinced that we have the technology for fixing them all. Yes. Okay. Sorry, John. Go ahead.
No worries at all. I just wanted to comment, like, does this feel consistent with proofs that are initially accepted and published, but then like maybe afterwards there's a serious flaw, and then like maybe afterwards, actually after this flaw is like discovered, they get repealed or rejected, or the idea becomes kind of broken down. Does this idea feel consistent, or do you think that's like a special case, or just wanted your thought on that?
Yeah, right. Yeah, so it's actually pretty interesting that like retractions are almost never happen in math journals. That is just like not really a thing, except maybe in like a few like super egregious cases. But sort of, I guess the thing I want to say is that there's sort of a spectrum from small mistake to really big mistake. Sometimes a proof makes it into publication, and people realize later that there was a really, really huge flaw, and that maybe the proof shouldn't have been published in the first place. And I think what usually happens there is like rather than the journal issuing like a retraction, it just sort of becomes sort of folklore in the relevant discipline that this proof isn't reliable. But I think most of the time, there's hope that you can find some way to fix the mistakes and figure out what went wrong, and people just continue sort of trying to do that. If it's big enough to like warrant publishing a new proof, then you'll do that. Otherwise, at some point, a new better proof is going to make it into a textbook somewhere, and then people will just talk about that one instead. Yeah, Jared, yeah.
Yeah, so I'm not entirely convinced at this point yet. And I'm not sure if it's just a matter of like semantics. Because like if a proof has a small error in it that's straightforward to fix, then I feel like it's not strictly that proof that people are accepting. It's the collective mental correction that people are accepting, right? So it is a corrected proof that's actually the accepted one, not the broken fixable proof in that case. And then you have the cases where you have proofs that have flaws, but the flaws aren't known. So you can't consider the flaws because any proof, no matter how rigid, could, no matter how strong, could probably still be flawed. So like that's like a non-starter. In the case of a serious flaw, maybe this is a question then regarding the finite simple group theorem. Are there known substantial issues with it that have yet to be corrected, and it's not even immediately obvious how they'll be corrected?
I guess it depends on what you mean by immediately obvious. My understanding is that people are still very much in the process of working over the original proof text, which again is like spread over thousands of pages in all of these different journals. And there's a bunch of known mistakes that as far as I know, have not actually been fixed yet. But I think my sense is that, you know, everybody pretty much agrees that none of those should be insurmountable. So I do think this is an interesting test case here, because if you want to say something like, well, they're not accepting the published proof, they're you know, accepting some sort of cleaned up version of the proof where all the mistakes are fixed, that is, like, you know, exists in people's minds or exists in the literature somewhere. This does seem like an interesting, you know, potential counterexample to that, because this does seem like a case where there's certainly not any proof in any one person's mind, because the proof is just way too big. There's also not a proof out there in the literature yet that has the mistakes all fixed. So maybe, you know, I see what you're saying, and it seems like maybe you can defend something along those lines, but I think it's going to be more complex than what you suggested.
Right. I think if I can, I don't want to take too much time, but I think there's a secondary point to this notion of acceptability, that there's different kinds of functional acceptance of a theorem, right? So the P versus NP, for example, for the most part, people operate under the intuition that P probably doesn't equal NP. We haven't proven it, but experiential evidence points to them being different. So there aren't any theorems out there that say, because P equals NP, or because P doesn't equal NP, we can deduce this. But there are certainly things that in the literature that I imagine say, because P probably doesn't equal NP, we can operate within those boundaries and we can be reasonably okay about it.
Yeah.
And I feel like there's a distinction between those two, sort of this experiential evidence towards something being true so you can operate roughly within those parameters, versus cases where literally it's not. So again, this counterexample of the classification theorem is very interesting, and I would want to learn about it in more detail maybe, because I'd be curious to see if it means that we don't have a known correct proof of it. But are there still papers that say, given this theorem as a known correct premise, we can deduce this, even though it's not known to be correct? Does literature using it, treating it genuinely as true when we don't actually know that it's true, exist?
Sure. So I think so there's certainly literature that treats the theorem as a known theorem.
Okay.
I think people would reject the characterization that we don't know that it's correct. I think many mathematicians would say we do know that it's correct, even though we haven't actually fixed all of these mistakes yet. But yeah, we should. Yeah, I'm already getting close to the end of where I should be.
Yeah. Go ahead.
So let me let Don talk here too.
Yeah, this really quickly. As you might expect, I'm sort of like happy with the idea that BF proofs are acceptable. That sort of grist for my mill. But I just wanted to check whether you would be happy with the way I was thinking about it, because I think I would have said something slightly different in response to John's question. Because I was sort of thinking about the BF proofs sort of by analogy with the proofs with the gaps, that you have these cases where for whatever reason the author doesn't write down, or maybe didn't even work through themselves all the details, and they say it is easy to see that blah blah blah, and you could, and so that seems like a case where, I mean, I don't understand completely how the epistemology works, but it seems to be that there's something about like their expertise as mathematicians gives them some grasp on whether or not the details can be filled in. And so so I was sort of thinking about the BF proofs in this sort of analogous way, that I'm not totally 100% sure that that this is correct in all details that you're telling me, but I can see, given my expertise, that we'd have no problem fixing anything up. So it's the same sort of expertise going on there. And so I think, so then I would have thought that in response to like John's question, that it's just that sometimes as we work through things, we find a mistake and we go, oh, that's beyond what I was, my intuition misled me in this case. So yeah, we do need to retract now until we fix it. Like with the Fermat's last theorem, that's presumably what was going on. So so my basic idea is it's the same sort of, expertise based intuition. But of course it's fallible, and sometimes it goes wrong. We realize, oh, we need to step back.
Yeah, so I flipped ahead to the slides about gaps because I think this is an important comparison. In fact, if you like the thought that mistakes of the kind that I'm interested in are just like gaps of the sort that mathematicians don't seem to have a problem with a lot of the time, that would be another possible way of resolving the tension, because then we would wind up with a conclusion that maybe broken proofs are transferable after all, because again, nobody seems to doubt that proofs with gaps can be transferable. So maybe proofs with mistakes can also be transferable. So let me quickly say something about why I don't think that's right in general. Right. So Kenny also points this out in his original paper, right? So he says, a proof sketch can in many cases be sufficient for the reader to convince herself of the result. So a proof with gaps will be transferable as long as the gaps are ones that relevant experts can see and still be convinced. So I think that's right. And you might think, well, mistakes maybe are the same sort of thing. As long as a relevant expert can see the proof and still be convinced, maybe it's still transferable. Okay, so briefly, the reason I don't think that's true in general is that I think usually the kinds of gaps that we find in sort of standard cases are ones where the gaps are sort of specifically chosen to complement what experts already know, right? So it's very straightforward for a typical expert to know what is missing and how to fill it in with sort of minimal effort and minimal creativity. And that is what I think isn't true for broken proofs in general, right? Because, since there's a mistake, the author generally didn't sort of purposely choose to make the kind of mistake that would be straightforward for a reader to fix. Sometimes fixing the proof will require resources that go beyond what's contained in the proof and the background knowledge of the typical expert. So that is in brief my argument for why, at least in a lot of cases, broken proofs are not going to be transferable, and brokenness is not exactly the same sort of thing as a gap. But I think that's an important point. Okay, so I realize that I'm already it's 4:43, so let me just very quickly wrap up. So like I told you, the option that I want to embrace in the end is this last one. I want to deny the transferability thesis, and I want to instead suggest that some acceptable proofs are not transferable. So if, given that I've argued that all the other options are wrong, this one had better be right, or else we're in some sort of paradox. Fortunately, I think it is right. Okay, so in view of the stuff that I said, I think the problem with the transferability thesis is as follows. It isn't that an acceptable proof is one that a typical expert would find satisfactory as is, as the transferability thesis sort of suggests, but rather it's one that an expert would judge to be correct in outline and fixable where it's broken by the relevant community using the methods at their disposal. So I think acceptable proofs need not be transferable, right? You might need something beyond your background knowledge to be convinced of the correctness of a broken proof, but rather only what I'm calling corrigible. So this is closely related to the notion of fixability. One difference is that a corrigible proof has to be correct in outline at least, which isn't a requirement for the notion of fixability. So that's one difference between what I'm talking about and what those guys are talking about. Okay, and finally, let me just note that I think what Kenny wants to say about transferability is not totally misguided. I think maybe it makes more sense to think of his notion of transferability as really comprising two distinct properties. And only one of those properties, I think, is genuinely required for acceptability. So the first property is that you need to be able to independently check all of the steps of the proof. And I think that one is right. I think he's right that an acceptable proof has to be evaluable in this sense. There can't be some like mysterious black box that you can't peer into, that you just have to take on faith. The other thing that sort of follows from his definition is that the proof has to contain all of the necessary information so that a typical expert with their background knowledge can become convinced. So you can call that impeccability. So in other words, there's nothing wrong. That is the thing that I think is problematic. I think he's right that acceptable proofs have to be evaluable, but I think he's wrong that acceptable proofs have to be impeccable. I think this weaker notion of corrigibility is the right one here. Okay, so if you want to ask me about why this sort of standard makes sense, we can talk a bit more about that. I have a bit of a story to tell here about, why is it that we don't just, buckle down and insist on getting rid of all of the mistakes? Why are journals so lax about letting in proofs that contain errors? I think there's actually a good epistemic reason for that. So feel free to ask about that if you want, but otherwise, thanks. Sorry for going a little long.
No, that was wonderful. Thank you so much. I think we should go ahead and open it up to Q&A. I think you're going to get a lot of questions. Maybe I'll just start us off with one, which would be, I do interactive theorem proving in like an interactive theorem proving environment. And I often have mistakes in my proofs, but it's a totally different type of mistake, which is that I will have proven something different than what I thought I'd proven, right? Like my proofs are always correct because the computer checked them, but then I might have proven something different than what I intended to prove. I wonder if does that fit into your framework, or would you think about that differently from a philosophical perspective?
I don't know, maybe it would help for you to sort of walk me through how this might arise. So it's like you're in your lean or whatever, and you're sort of trying to translate the steps of your informal proof into the formal language.
Yes.
And you just like don't quite like do the translation right. And so
yeah, for example, it would often be the case with me that I have to encode something that is set theoretic using types. And there might be some subtle mistake that I make when I do that. And as a result, the type that I come up with does not perfectly encode the sets I was thinking of. It might be like there's a huge amount of overlap, but it's a little different. And so then it's usually the case that the proof idea I have, once I find the error, I can change it a little bit so it applies still. But it just feels different morally to me because it's like there wasn't actually a mathematical mistake. There was like a philosophical mistake. Like I just didn't prove the thing I wanted to prove. You know what I mean?
Yeah, interesting. That is interesting to know. It's definitely on my list of things to do as a philosopher, to learn more about automated theorem proving and proof assistance. So that's interesting to know that this is the kind of issue that people encounter often, because it sounds like Jared had the same issue. So yeah, I mean, that's really interesting. I mean, I guess the obvious thing to say is that, like you said, it's not really a mathematical mistake. You have a correct proof in the end of a different statement, and there's nothing to complain about, with that proof. But if you want to like push more on anything and suggest that maybe, there's more for me to say about this, then go ahead. Otherwise, Don.
Okay. Yeah, I wanted to go back to the follow up a little bit more on the gap issue.
Yeah.
So I guess I guess I don't really disagree with what you said about there being an important difference between gaps and these sort of broken proofs, and I don't disagree with the claim that as a result broken proofs don't end up being transferable on Kinney's definition. And so yeah, so that might make people that want everything to be all done not happy about this. But I guess my only point was that it seemed like that if you dug into the epistemology of it, it's another case where we're relying on the intuition of experts as to whether such and such can happen, and that there's a parallel at that level.
I see.
Or do you disagree with that? Because that was sort of my question.
Yeah, no, I think that's right. I mean, it's an intuition that is usually guided by lots of experience and usually quite reliable, I assume. But yeah, I mean, ultimately there is some sort of practical competency there that is like what is doing the epistemological work. I think that's right. Okay. You as a referee can say like, yeah, I haven't really thought this through, but I've seen plenty of other arguments that look a lot like this, and like this is the sort of situation where I would expect this lemma to apply, and no particular reason to be suspicious. So yeah, and I think that is the same, at some level of description, it's the same sort of thing as seeing a gap and thinking like, yeah, I probably would know what to do there. I don't really feel like thinking about all the steps, but yeah, that seems fine.
Okay. Cool. Thank you.
Jared.
Yeah, so I thought I'd comment some more on the interactive theorem proving side of things.
Okay, yeah.
Because yeah, I was having a conversation with people just this week about it, because we had a professor who asserted that he believed that like computerized proofs are going to be like the future of all mathematical literature, which I think people have been saying for decades, and it hasn't happened. I'm
skeptical as well.
Yeah, I'm skeptical if for no other reason. I mean, like, I'm a computer scientist first and foremost, but I certainly appreciate the aesthetic value of the handwritten proof. With regard to this particular topic of transferability and fixability, I think it's interesting because mechanized proofs, you can, I guess, I don't know how theorem provers are written under the hood. I'm hoping to learn more about it, but presumably you can't be certain that the underlying implementation is even correct. But as long as you're extremely confident that the underlying implementation is correct, the way that Coq is used and the way that lean is used, like, people assume that it's correct under the hood. So let's assume that it's correct under the hood. Even still, the proofs, so one, to Max's point, like, you can accidentally encode the wrong thing, right? So the translation between paper and computer was wrong. And it's even worse because on the literature side, people are not going to go look at the Coq code nearly as likely as they are going to look at a proof on paper. But on top of it, computerized proofs are often really opaque. And even if they're more confidently correct because they type checked or whatever, you have no idea what's going on in the thick of it. And there's definitely something lost there in a couple of respects. And you can almost ask the question of, like, what's more important, having proofs that might have flaws but it's human reason throughout the whole thing, and you can find the errors and you can address them and you can comprehend it, or proofs that you can be nearly certain, like even higher degree of certainty are correct and don't have small issues, don't have small flaws, but you have no idea how the proof worked.
Yeah.
Obviously there's room for both, but it's, I think it's something worth exploring. And I think you mentioned like you'll want to look more into theorem proving stuff. Like I think there's a lot of room, because there is sort of I think a boom in that right now, particularly with lean. So it'll be interesting to see how that evolves in the
yeah, totally.
Yeah, so this is, I completely agree with Max on this, that there are absolutely, like, when I'm working on like cock proofs that are, I've been doing ones this week that a given proof is like over 100 lines long, which maybe that's short for seasoned cock users, but for me, that's like a really long proof. And I have no idea what's going on. Like, I'm basically just throwing spaghetti at the wall until it works. And then eventually it works. And I'm like, great, but I didn't learn. What did I learn? Right? What did I learn? And what will anybody after me learn? I think there's an extent to which it can be a little detrimental to the mathematical, like the discipline as a whole.
Yeah, that's great. I just sent a paper in the chat. I don't know if you guys know this paper, but this is sort of a classic philosophy of math paper by Rav called Why Prove Mathematical Theorems. And he says some related things that I think are really interesting. So he imagines, we have some super powerful oracular computer where we can ask it any mathematical question and it'll give us the correct answer, yes or no. Is the Riemann hypothesis true? It'll tell you instantaneously without fail. You might think, from a very naive point of view, that would be like the greatest thing ever to happen in the history of math, because then we could have all of the mathematical knowledge at our fingertips. But he argues this would actually be, not only not as helpful as you would think, it would be actively harmful in many ways, because the thing that we want isn't just to know that a theorem is correct and to know that a correct proof exists. What we want is something more like understanding. Ultimately, that's what math and maybe science in general is really all about. That's like the fundamental epistemic goal, not just knowledge, but understanding why things are true. And it seems right that if we come up with proof assistants that can sort of help you write down, or maybe even autonomously write down some proof that is totally like inscrutable to a human, even if you're quite sure that the proof is right, but you can get no insight out of it, it's very unclear that that would be a good thing. So I think that paper is an interesting one to look at if you want to think more about that sort of thing. It's a pretty old paper, like it's from the like maybe 80s or 90s, so definitely like pre-AI and pre-automated theorem proving, but it's a good one, yeah. So I mean, I guess on the other hand, I've heard in some places that using these kinds of proof assistants maybe can also increase understanding in certain ways. Like I think there's a famous case of Peter Schulze where he was trying to sort of translate some proof into a proof assistant, and he realized that there was like some important part of the proof that he hadn't thought through completely clearly. And the sort of effort of trying to formalize that part of the proof made him understand much better what was actually going on there. So I don't want to say that, it's all bad to work with computer assistants, because I think, there are ways in which they can be epistemically useful, but to the extent that, they just become these sort of inscrutable oracles, then that plausibly wouldn't be very good. Yeah, Don.
Yeah, I just as long as I've got you here, or we've got you here, I wanted to ask about the probabilistic proof stuff. You have like one line in the paper, like this is not this is orthogonal, but I just so just for my own purposes, like I'm, like I wrote a reply to Kenny saying, yeah, transferability, that's a great concept. It does seem like it distinguishes the proofs we like from the probabilistic proofs we don't like. But what value is it providing? And I sort of made an argument in my reply that it doesn't point to anything kind of epistemically valuable that you can't also get from probabilistic proofs. And so I was just wondering whether you had any thoughts about how the corrigibility, if there's more to be said for corrigibility than that, or because I mean I guess what was spurring me on is that, like, I read the last section of your paper where you give the argument for it in terms of the kind of epistemic consequentialism that we're trying to maximize true beliefs and minimize false beliefs and so forth. But if that's all you care about, then probabilistic proofs, why not go for it? So I was just wondering whether you had ideas for anything more to be said for corrigibility to answer my question. I mean, this not that you haven't perfectly well responded to Kenny, but
yeah, no, that's also a great question. I'm sorry that I just actually realized that you have this newer paper. I know the original ones, but somehow the fact that that there was also this response to Kenny, it's in like an edited volume or something. Is that right?
Yeah, it was. Yeah, I didn't publish it in a big enough venue. That's clearly a problem.
Yeah, I actually did not know that this existed and have not read it. I just discovered it earlier today, in fact.
Oh, okay.
So,
well, I'll give you some time to look at that then, and you tell me if you
yeah, I mean, I do think it's a really interesting question, and I think I may have some thoughts about it, but maybe I'll send you an email.
All right, sounds good. Thanks.
Maybe just a plug for the utility of the more experimental side. In the ACL2S world, which is a theorem prover that a lot of us use at Northeastern, many of us work on a principle of testing our conjectures before we try to prove them. And ACL2S has built-in conjecture testing capabilities. I realize it's a little different because the enumerator might not be guaranteed to cover the distribution in a manner that gives you any particular probability of correctness. But just empirically speaking, like a lot of us find that it is very useful to do a few minutes of random testing on a conjecture before we invest days into trying to prove it, right? So
totally,
yeah, there's some synchronicity there that is interesting.
Yeah, I mean, I don't think anyone would deny that, like, gathering this kind of inductive experimental evidence is really, really useful. Even if you don't think that it ever takes you to the level of knowledge, it would be crazy to deny that, it's a really important part of like mathematical practice, and it plays a really big role in deciding what is even plausible and what is worth trying to prove in the first place. Yeah, that seems right.
Bill, we've kept you for over an hour. This has been super interesting, and I'm sure that people are going to want to follow up and email you questions, not just Dawn, but probably others as well. Is that okay? What's the best way to contact you, etc.?
Sure. Yeah, that would be awesome. Yeah, so my LMU email should still work. They haven't pulled the plug yet. I'm sort of in between jobs at the moment. I'm going to be heading to Oxford in a few weeks, but I don't yet have my Oxford email. But you should be able to use my my Munich one. So
awesome. And just to be clear, it's fine with you if I post this recording so people can watch it after the fact, right?
Sure.
Okay, excellent. Well, thank you so much for joining us. This was a ton of fun, and I think, particularly cool that it related directly to work from somebody from the institution that most of your audience happen to be from. And we really appreciate that you took time out of your weekend to come and talk to us. This was fantastic.
Yeah, thanks, guys. Thanks for the great questions. Is there like a mailing list or something for this group that I can get on?
Yeah, we have a Slack, and then also if people request to get notifications, I run the group with a friend of mine named Jacob, and the two of us manually notify people based off what they're interested in. So if you say like, I'm more interested in the security talks, or I'm more interested in the math talks, we'll notify people who we think fall into whatever category the next event is on. But the Slack is the easiest way to stay updated. So yeah, I'd be more than happy. I can email you after this to add you to our notification list if you're interested.
Yeah, that sounds good. Cool.
Okay, awesome. Thank you so much. Talk to you later, Bill.
Okay, thanks.
Okay.